Hey folks, let's finish off section 11.2. So this is the second part of section 11.2 where we're looking at power series and properties of power series. Now there are a lot of advantages to representing functions as power series. First off, a power series kind of looks polynomial. I mean, it's polynomial in nature. It just has an infinite number of terms. Arguably, the easiest functions to differentiate and integrate are polynomials. So that's an advantage. This next theorem I'm about to show you is pretty powerful. It's going to allow us to create power series for functions using a known function and its power series via differentiation and integration. So we're gonna start to create things, and it's pretty cool and it's pretty powerful. So here's the theorem. If f of x is given by this power series centered at C, and if f of x has a radius of convergence r, notice just by saying it has a radius of convergence r, this implies that there does exist an interval of convergence. Then on the interval, c minus r to c plus r, no claim about the endpoints, the function f, it is continuous, it is differentiable, and it's integrable. In fact, the derivative, f prime of x, well, if you do term-by-term differentiation, the derivative of a sub 0 would be 0. The derivative of a sub 1 times x minus c, that would just be a sub 1. The derivative of a sub 2 x minus c quantity squared, well, that would be 2a sub 2 times x minus c, etc., etc. That ends up equaling, now look at the series notation. So I just talked about the term-by-term differentiation, but look at the series of the function. F of x is the series n equals 0 to infinity, a sub n quantity x minus c to the n. A sub n is just a generic constant. So when you differentiate a sub n quantity x minus c to the n, you just use the power rule. N comes out front, subtract 1 from the exponent. So rather than go through term-by-term differentiation, we can differentiate the series notation itself and say that f prime of x equals the series n equals 1 to infinity, n times a sub n quantity x minus c to the n minus 1. Likewise, when you integrate, f of x, well, I could go through and do term-by-term integration, and we know when we integrate, an indefinite integral, we're going to get a generic constant of integration. So I'm starting off the term-by-term integration with my constant c. But you do term-by-term integration, and you get c plus a sub 0 x minus c plus a sub 1 x minus c squared over 2, etc., etc., which is equal to c plus, well, just like with differentiation, you don't have to do term-by-term integration. You can just simply look at the series notation itself for f. So the series notation for f was the series a sub n quantity x minus c to the n. So crank it through the power rule for integration. So you'd add 1 to the exponent. That gives you x minus c to the n plus 1. And the little multiplier out front would be 1 over n plus 1. So that's how we come up with the integral of f of x dx equals c plus the series a sub n quantity x minus c to the n plus 1 over n plus 1. Now, before I go any further, when you integrate a function that's represented by a power series, that plus c, that is absolutely irrelevant. And I'm not going to include it going forward. We're talking about an infinite series, so a little constant added in there, absolutely irrelevant. So here comes a big 3-star comment. Your function f, the derivative, and the integral, all of them have the same r. That is, they all have the same radius of convergence. Now, they may have a different interval of convergence, so the interval of convergence for each of them may be different, but they're only going to differ at the endpoints of the interval. This is a really, really powerful theorem. So let's just practice this theorem. So consider the function f of x equals, there, I'm giving it to you in series notation, x to the n over n. We're going to determine the interval of convergence for f, in part B, f prime, and in part C, the integral of f of x dx. So we'll not only do the interval of convergence for each, but we're going to come up with the series notation for each of them. So, you know what? Let's head off to the chalkboard and crank through this example. All right, folks, in this example, you were given this power series, x to the n over n, and you were asked to determine the interval of convergence in part A for the function f, part B for f prime of x, and part C, the integral f of x dx. In parts B and C, we'll also list, what the power series is for f prime and the integral of f, respectively. So here we go, interval of convergence for f. Remember, your near dear friend in coming up with the interval of convergence is the ratio test. So the ratio test, P is the limit as n goes to infinity, absolute value of a sub n plus 1, so that's x to the n plus 1 over n plus 1, then divided by a sub n, so divided by that, and you know I'm going to rewrite that as n over x to the n. So we get the limit as n goes to infinity. I'll rewrite this. And just kind of cleaning up stuff here. X to the n plus 1 over x to the n. That simplifies to x. And so we're just looking at the limit as n goes to infinity. So you're probably recognizing I'm going to divide everything in the numerator and denominator of this fraction by n. And so when we take the limit, we just get absolute value of x. So that's what P is equal to. So we know we have convergence with the ratio test. When P is less than 1, that's when absolute value of x is less than 1, which gives us that compound inequality, -1 less than x less than 1. So just going to make a note. Right here, I know my radius of convergence is 1. I'm making that note because that theorem that we just looked at said that for this function that's given by this power series, if we do the derivative has the same radius of convergence. If we do the integral has the same radius of convergence. But now let's get the interval of convergence. So remember, with interval of convergence, you have to check the endpoints. And when you check these endpoints, let's see, when we check x is -1, that gives us the series -1 to the n over n. What do you think? Does that converge or diverge? That's right, it converges. Why does it converge? Well, you could say alternating series test, or you could say, it converges because it's the alternating harmonic. When x is equal to 1, that gives you the series 1 to the n, which is just 1 over n, which that diverges. Why does that diverge? Because it's the harmonic series. So for part A, Our interval of convergence is a square bracket around -1 and a parenthesis around 1. So that's the deal for part A. Part B, so now bear with me as I erase the board here. Part B, part B was get the interval of convergence for f prime of x. So let me continue to erase this here. I'm just going to make a note up here in the corner. From my work in part A, I know for part B, I know my radius of convergence is going to be 1. And we'll just have to check the endpoints. All right, well, first off, the derivative. Folks, we don't have to write down all the terms of this and do term-by-term differentiation and then try to write down, what the power series notation is. We can just do the derivative of this. Remember, your n. N is nothing more than a constant. It's a number. So you only have the variable x being raised to the nth power. So when you differentiate x to the nth power, it's just the power rule. N would come out front. You'd subtract 1 from the exponent, which hopefully you would say, well, the n's cancel out, so it just simplifies down to x to the n minus 1. This is the series notation for the derivative. So once you know the series notation for the derivative, and you know the derivative has the same radius of convergence as the function, all you have to do is check the endpoints. I mean, the radius of convergence was 1. I mean, it's centered at 0, so you just need to check the endpoints. You need to check x equals -1. So you put -1 into the derivative, the x to the -1, put -1 in there. That gives you the series -1 to the n minus 1. Folks, that diverges. Fails the nth term test. Put 1 in. So you put 1 in here and you get 1 to the n minus 1. That just simplifies down to 1. That diverges. The nth term test. So the interval of convergence for the derivative is -1 to 1, parenthesis around both. So it was easy for us, given the function, it was easy for us to get the power series for the derivative, and then it was easy for us to determine the interval of convergence because we did all the work in part A determining the interval of convergence for the function itself. So we knew we had to get the radius of convergence along the way. So part C, bear with me as I erase the board here. Part C was dealing with the integral f of x dx. So in part C, well, the integral of f of x dx. Okay, that is, folks, we don't have to write down all the terms of that series and do term-by-term integration. We can integrate the notation that's in the power series itself. X to the n. When you do the antiderivative of x to the n, you add 1 to the exponent and then put the reciprocal of the new exponent out front. So when you integrate this x to the n, I mean, if it helps you, you can see this as a 1 over n x to the n. That's just a constant. So when you integrate, you would have a 1 over n times, add 1 to the exponent, and then out front you put the reciprocal of that new exponent. Now I personally would write this series as x to the n plus 1 over n times n plus 1. I just think that looks a little more compact. That looks nicer. So I would encourage you to write it like that. Again, remember, the function, the integral, the derivative, they all have the same radius of convergence. Because they all have the same radius of convergence, we only need to check the endpoints. And the endpoints are -1 and 1. So we check the endpoints. So when x is -1, that gives us the series -1 to the n plus 1 over n times n plus 1. So now, does that series of constants, does it converge or does it diverge? Well, you should be able to verify that it converges, and the reason why is the alternating series test. When x is 1, so you put 1 in here for x, you get the series 1 over n times n plus 1. Does that converge or does that diverge? Well, you should be able to show that it converges. I mean, I personally would compare that series, 1 over n times n plus 1, I would compare it to the series 1 over n squared. That's a p-series that we know converges. And I would either do the limit comparison test or the direct comparison test. So we now know that the interval of convergence for the integral is square bracket -1, 1 square bracket. All right, I don't have an example for you to just practice this. As we go through this section and examples that are coming up, this concept will be embedded in those examples. Sometimes you can take the derivative of something you know or take the antiderivative of something you know. So it'll be embedded as we move on. But at this time, let's head back to the slides and see what's next. All right. Moving along, our next task is going to be representing functions by a power series. In other words, we are going to study how to find a power series to represent a function. And in doing so, we're going to revisit an old friend of ours, the geometric series. So let's see the mechanics of how we do this by working through an example. So here's the example. Let's find a power series for f of x centered at c equals 0 and determine the interval of convergence where the function is 3 over 4 minus x. So write it down. You know the drill. I'm going to head off to the chalkboard to work through this. All right, I told you we're going to start to encounter stuff where we're going to go back and revisit our good friend, the geometric series. So in this example, you were asked to determine a power series for the function f centered at c equals 0 and also get the interval of convergence. And the function you were given is 3 over 4 minus x. So 3 over 4 minus x. Now I made a little note over here. Recall this was the general form of a geometric series. We know the geometric series converges. In fact, it converges absolutely when the absolute value of r is less than 1. And when the absolute value of r is less than 1 and it converges, we know the sum of the geometric series is a over 1 minus r. So the sum is a over 1 minus r. A over 1 minus r. Let me kind of start with that. Let me write this down as kind of like a goal. Is seeing an a over 1 minus r. Well, look at the function you're given. You are given 3 over 4 minus x. That kind of looks like an a over 1 minus r. Really, the only difference is here's a 1 and here's a 4. So how could I turn this 4 into a 1 legally? Divide everything in the numerator and the denominator by 4. If I divide everything in the numerator and the denominator by 4, I get 3/4 over 1 minus x over 4. This is exactly in the form a over 1 minus r. It's exactly in the form where we can now say, well, look at this. A is 3/4. R is x over 4. So if you have a is 3/4 and r is x over 4, your function, where did it go? Your function, 3 over 4 minus x, putting it into the geometric series. I mean, right here. That's what we remember about geometric series. It's the geometric series. A is 3/4, r to the n. So that's x over 4 to the n. Now I know that there are some people that could write this differently. I'm just going to leave it. I'm just going to leave it like this, because my next step is, well, that's great. I have the geometric series. I have the power series that represents this function, but what is its domain? What is its interval of convergence? On what interval is this power series exactly the same as this function? So I need to determine the interval of convergence. This doesn't take too much work because we know a geometric series converges when absolute value of r is less than 1. R is x over 4. So we know we have absolute convergence when the absolute value of r is less than 1. That's absolute value of x over 4 is less than 1. Negative 1 is less than x over 4 is less than 1. Multiply everything by 4. You get negative 4 is less than x is less than 4. And there's no need to check this at the endpoints because that's built into the geometric series test. We know that if negative 4 is in here for x, it diverges. We know if 4 is in here for x, it diverges. Because the geometric series test that we saw way back in section 10.3 told us the geometric series diverges when absolute value of r is greater than or equal to 1. And at those endpoints, r would be, the absolute value of r would be equal to 1. So for this power series, so here's our answer. The function 3 over 4 minus x is a power series representation of 3/4 times the quantity x over 4 to the n and the domain, or the interval of convergence, is negative 4 to 4. That means on the interval negative 4 to 4, just on that interval, negative 4 to 4, this function is the same thing as that power series. And a cool thing you could do, and I might do this later on, but not for this one, you could write down, say, the first 5 terms of this power series. So you could write down the first 5 terms, and you could put in your calculator you could put this function in y sub 1, and in y sub 2 you could put, say, the first 5 terms of the power series, and on the interval -4 to 4 you could graph both of them to see how well it does fit, how well it does match up. And of course you would get better and better and better fitting by adding more and more terms. So maybe you'd add, the first 8 terms. I may look at that later on in this video. But here's what I'd like you to do right now, just to practice this idea, this example, how the geometric series is our friend, it can be a goal. I would like you to do from the section 11.2 supplement number 2, I would like you to do number 6. And I have a hint for you as you try number 6. In number 6, since you're being told to center it at -3, well, to center it at -3 means somewhere in your trying to get to the goal to see an a over 1 minus r, you're going to have to see an x plus 3 inside parentheses. So that's my hint. Go try to do number 6. So pause the video, do number 6 from the supplement handout. When you're done, restart the video. I'll be here at the board cranking through it. Okay, folks, here in number 6, you were given the function 4 over 5 minus x. You're asked to get a power series centered at c equals -3. Also get the interval of convergence. And I gave you a hint, so let me write that down. When I see c as -3, that tells me that I need to see, eventually, I need to see an x plus 3. Because remember with the power series, that general form is, the quantity x minus c to the n. Well, if x minus c, if c is -3, x minus a -3, that's an x plus 3. Next, I know my goal is to see an a over 1 minus r. So let's begin. Look at my function. My function, 4 over 5 minus x. I need to get it to this goal, but at the same time, I need to see an x plus 3. So I can't just start off and I'd say, let's divide everything by 5 and I'm done. I'd have 4/5 over 1 minus x over 5, because I need to see this x plus 3. So here's what I'm going to say. Put down the 4, that's in the numerator. You need to see an x plus 3. So in the denominator, let's go ahead and put in an x plus 3. Notice how I wrote that. You notice how I've given myself some space. Okay, I need, whatever I end up writing in here in the denominator, it still has to equal a 5 minus x. Can't change that value. So first things first, there'd be a negative sign in front. Okay, you know what? Let me go ahead and put the 5 in. I see the 5, so let me put the 5. Is this denominator the same thing as 5 minus x? No, it's not. Because I'd have 5 minus x minus 3. 5 minus 3 is 2. So this denominator right now is 2 minus x. It's not 5 minus x. So what do I need to put in here? To preserve that this denominator is equal to 5 minus x. That's right. I need to put in a plus 3. I mean, think about it. When I insert it into the denominator, the x plus 3 inside parentheses, and I put the minus sign out in front of it, so I'd have a negative x minus 3. To neutralize that minus 3, I have to add 3. Go ahead and check. This denominator is exactly the same as that denominator. which means this fraction is exactly the same as this fraction, which means 5 plus 3 is 8. And now to get this into the form a over 1 minus r, I mean, that's the goal. And the key part of the goal is getting a 1 there. So how do I turn this into getting a 1 in that position? Well, quite simply, divide everything in the numerator and denominator by 8, because 8 divided by 8 is 1. So when you divide everything by 8, so 4, the numerator, 4 divided by 8, okay, that's a 1/2. The denominator, 8 divided by 8 is 1. X plus, well, I'll write that as just x plus 3 over 8. But notice that what we have right now, this is the form. We want this to be in the form a over 1 minus r. So just place by place comparison. A is 1/2. R is x plus 3 over 8. So I should be able to write the power series. Because I know what a geometric series looks like. A is the series A, R to the n power. Now there are many ways to rewrite this. I'm just going to write down one more way to rewrite it. I'm okay with this. I'm happy with this. But I could write this whole thing as x plus 3 to the n over 2 to the 3n plus 1. It's like, where in the world did that come from? Well, keep in mind 8 is 2 cubed. And there's a property of exponents that says when you have a fraction to a power, it's numerator to that power over denominator to that power. So if 8 is 2 cubed to the n, that would be 2 to the 3n. 2 times 2 to the 3n is 2 to the 3n plus 1. Like I said, I'm happy with this. And, let's get the interval of convergence. We know it converges if absolute value of r is less than 1. Well, since r is x plus 3 over 8, that gives us x plus 3 over 8. Absolute value of x plus 3 over 8 is less than 1. So negative 1 is less than x plus 3 over 8 is less than 1. Multiply everything by 8. Subtract 3. So we know the interval of convergence is negative 11 to 5. And you can quickly check that negative 3 is the midpoint of the interval of convergence. So our function, 4 over 5 minus x, is exactly equal to that power series on the interval negative 11 to 5. That's pretty cool. We're creating stuff here, which I just find to be absolutely cool. Just using a little bit of information, we are creating some powerful stuff. So why don't we head back to the slides and see what is next.
All right, in that example, hopefully you saw how the geometric series was our dear friend, and remembering the sum of a convergent geometric series was a key goal in doing that example. And then in number 6, gave you a little bit more practice. So next up is another example. Let's find a power series centered at c equals 2 and also determine the interval of convergence for the function f of x equals 3 over 2x minus 1. So write this one down because I'm heading off to the chalkboard to work through it.
All right, folks, in this example, we're asked to find a power series for the function 3 over 2x minus 1, and we want it centered at c equals 2. Also determine the interval of convergence. So hopefully we're starting to get into the flow of things here. First, since we have c equals 2, that implies we need to see an x minus 2 eventually. Centered at 2, we better see an x minus 2. Second, remember our goal. A over 1 minus r. So we're going to take our 3 over 2x minus 1, and we're going to try to get it into this a over 1 minus r. So let's see. Well, I know I need to see an x minus, or I need to see an x minus 2 because it's centered at 2. So let me, you know what, let me go ahead and rewrite this first, just to help me in trying to see this x minus 2. 2x minus 1, I'll just rewrite it as negative 1 plus 2x. All right, so, I know I need to see an x minus 2. So let me go ahead and tack that in here, x minus 2. And, well, since this denominator, it says that there's a 2x, I better have a 2 out in front of this parenthesis. So 2. It's a positive 2x, so that's a plus. Oh, and then I have my negative 1. All right, quick check. This denominator does not equal that denominator. They are not the same. So what do I have to do? What do I have to do here? What do I have to add in down here to make sure this denominator is exactly the same as this denominator? Well, if you're thinking, well, Bill, if you try to simplify this denominator, the first thing you would do is distribute the 2. So that gives you a 2x minus 4. You better come in here and add 4. If you're thinking that, you'd be absolutely correct. Go ahead and, if you clean up this denominator the way it's written right now, if you clean it up, you are going to end up with negative 1 plus 2x. So I think we're getting somewhere. See, negative 1 plus 4. Well, that's a 3. I think we're getting somewhere. Let me kind of pull this up to right here. We're almost in this form. Remember the key is seeing a 1, to see the 1 minus r. So I need to, divide by 3 to turn that into a 1. So I divide everything in the numerator and denominator by 3, and that gives me a 1 over 1 plus 2/3 x minus 2. I think I've hit the goal. So if right now you're saying, oh, no, you haven't, Bill, because the goal is a 1 minus r, and this is a 1 plus. It's not a 1 minus. Now, I've hit my goal. A is 1. R is negative 2/3 x minus 2. I mean, I can write this as 1 minus negative 2/3. Minus a negative is addition. So I think where we're at is that our function 3 over 2x minus 1 as a power series is a r to the n. A is 1, r to the n. Okay, now you could write that many different ways. I mean, you could say, well, negative 2/3, that's just negative 1 times 2/3. So you could write this as negative 1 to the n times 2/3 x minus 2 to the n. So you could do that. I'm happy with this. I'm happy with this. There are many ways to represent it. I'm happy with either one, but I need to get the interval of convergence. So remember, interval of convergence, we know for interval of convergence, we know in general the geometric series converges when the absolute value of r is less than 1. So even if you use this form where you're saying r is a negative 2/3 x minus 2, that's what you're saying r is. Keep in mind that's coming inside absolute values. So that absolute value of negative 2/3 would just be a positive 2/3. So let me just kind of cutting out a step here. And to rewrite this as negative 1 is less than 2/3 times x minus 2 is less than 1. Multiply everything by 3/2. Then add 2 to all the pieces. And when you add 2, I think you get a negative 1/2 less than x less than 7/2. So that tells you the interval of convergence is negative 1/2 to 7/2. So there's the power series representation for the function 3 over 2x minus 1. That's the interval of convergence. This function is exactly equal to this power series for that domain on the interval of convergence, negative 1/2 to 7/2. So, you know what? I'd like you to practice one more of these. So if we do, on that supplement, 11.2, supplement number 2, why don't you try number 12? So go ahead, pause the video, section 11.2, supplement number 2, try number 12. After you do number 12, restart the video. I'll be here at the board cranking through it. Number 12, you were asked to find a power series for the function 4 over 3x plus 2, and it was to be centered at c equals 3. So, first thing, c equals 3 implies I'm going to have to see an x minus 3. Then I write down my goal, a over 1 minus r. So here's my function. I know I need to see an x minus 3, so let me go ahead and get that in here. But you know what, I would rewrite this as 2 plus 3x. Alright, so now let me get that x minus 3 in here. So I have my x minus 3. Notice this is a 3x, so out in front of that it would have to be a 3. And it looks to me like in order to preserve what this denominator is, doesn't it look like I'm going to have to add 9? Because when 3 gets multiplied by negative 3, that's a negative 9, so I have to add 9 to neutralize it. You always know if you are correct at this step. Clean this up. Make sure you get the denominator of the function you were given. There's no sense going on any further if you don't know this is absolutely the same thing as this. And then, see, 2 plus 9 is 11. I think we're getting kind of close. I need to see, remember the key most important part is a 1. So divide by 11, divide everything in the numerator and denominator by 11. And that gives me 4/11 over 1 plus 3/11 x minus 3. So I can now see A is 4/11. R is negative 3/11 x minus 3. 1 minus negative. So the power series for the function. So our function 4 over 3x plus 2 has the power series representation of A, which is 4/11, R is negative 3/11 x minus 3 to the n power. And you know there are many ways you could rewrite that. I'm just going to put up one. And I'm happy with this. I'm fine with this. But see how I'm taking this, how I could take this and rewrite it as 4 times negative 3 to the n times x minus 3 to the n all over 11 to the n plus 1. I am not saying you have to go from here to here. I'm not saying that at all. I'm saying, can you see how to go from here to here? So we have our power series representation for the function. All that's left is the interval of convergence. Well, remember it converges. Geometric series converges if absolute value of r is less than 1. So that's absolute value. Absolute value of a negative is positive. So you'd have a negative 1 is less than 3/11 times x minus 3. It's less than 1. Multiply everything by 11/3. And then add 3. So that gives you a negative 2/3 is less than x is less than 20/3. So your interval of convergence is negative 2/3 to 20/3. So there's the function. There's the function as a power series on this domain. The function 4 over 3x plus 2 is exactly equal to that power series on that interval of convergence. So we've done quite a few examples now of seeing how the geometric series is our dear friend. So let's head back to the slides and see what's next. All right, hopefully that example made sense, and hopefully you were able to crank through and do number 12. Continuing on, next up is another example. We're going to find a power series centered at c equals 1 and determine the interval of convergence for, well, the function we're going to do first is 1 over x. That's part A. And part B is the function natural log x. And just kind of foreshadowing what's going to happen here. Look at the function in A and look at the function in B. Once we know a power series for the function in A, 1 over x, to get the power series for the function in B, natural log x, it looks like a little integration will come into play the game, because we know the antiderivative of 1 over x is ln x. But let's head off to the chalkboard and see how this works out. All right, this example, we're asked to find a power series centered at c equals 1, and I gave you two functions. In part A, I gave you the function 1 over x. Well, first off, c equals 1. That means I better see an x minus 1 somewhere. Thing 2, remember the goal. A over 1 minus r. So 1 over x, well, let's see. I have to see an x minus 1, so let me go ahead and put an x minus 1 in there. So if I put an x minus 1 in there, what more do I need? I mean, this denominator is not equal to that denominator. So I guess I would have to, what, add 1? Isn't that denominator now equal to that denominator? I think that's it. I mean, we have A is 1, R is negative x minus 1, 1 minus a negative. So it looks like our function 1 over x has the series notation of a r to the n. A r to the n. A is 1. R to the n. I think for this one you could see a lot of people, you could see why a lot of people would say, hey, we could just write this as, you know, a negative 1 to the n, x minus 1 to the n. I mean, that's pretty easy. But in any event, what's the interval of convergence? Well, remember, you have convergence when absolute value of r is less than 1. So the absolute value of r, absolute value is negative, is positive. So you're just left with this. And then add 1 to everything. So the interval of convergence is 0 to 2. All right, so note, because it's centered at 1 and we have 0 to 2, note this tells us the radius of convergence is 1. Why am I mentioning that? Well, in part B, you were given the function, weren't you given the function natural log x? Let me grab my paper real quick. Yeah, you were given the function natural log x. I should be able to use my work in part A to get part B just like that. And that's because we know the antiderivative of 1 over x is natural log x. So we can look at the 1 over x, we can get the antiderivative, and that will be natural log x. So let me write that down. We know the antiderivative is natural log x. And I know you're saying, oh, Bill, really it's the natural log absolute value of x. But we're talking about positive numbers here, so I don't have to worry about the absolute value. So let's integrate. Let's integrate this. And if you integrate this, oh boy, look at what you get. You get the series. I guess maybe I'll integrate this form. Because that's a negative 1 to the n is a constant. So negative 1 to the n. So it's just this I'm cranking through the power rule. So I would have x minus 1. I'd add 1 to the exponent, so that'd make it n plus 1. And then the little multiplier out front would be 1 over n plus 1. So that gives me x minus 1 to the n plus 1 over n plus 1. And technically, yes, there's a constant attached to that. There's a plus c somewhere, like a c plus, because when you do an indefinite integral, you get a constant of integration. But in the world of infinite series, that constant of integration is absolutely irrelevant. So let's see where we're at. Progress check. This is for the function natural log x. We came up with the power series for natural log x by integrating 1 over x. The power series for 1 over x, we integrated that to tell us natural log x. Now the interval of convergence, well, that's why I mentioned over here what the radius of convergence was. Because remember that theorem that we saw early in this video? That theorem said the function, derivative, and integral all have the same radius of convergence. And because they all have the same radius of convergence, the only place they could differ is at the endpoints. So the function had an interval of convergence of 0 to 2. The only place that the integral could have a different interval of convergence is at the endpoints. So you just need to check the endpoints. That's it. So if you check the endpoints, if you check x equals 0, that gives you the series -1 to the n, -1 to the n plus 1 over n plus 1. This would be rewritten, bases are the same, you're multiplying, add the exponents, you'd have -1 to the 2n plus 1. 2n plus 1 is always an odd number. So -1 to an odd number is just simply always going to be -1. And I know that series diverges. It's a form of the harmonic series. You know, just shifted one unit over times -1. I need to check x equals 2. So when I check x equals 2, see 2 minus 1 is 1. 1 to the n plus 1, well that's always 1. So we have the series -1 to the n over n plus 1, which is alternating. It's a version of the alternating harmonic series. So it converges. So here, for this function, the interval of convergence is parenthesis around 0, square bracket around 2. That's it. Starting to see a little bit more of the power, how we can create a power series for a function and then use calculus, differentiation, or in this case integration, to determine a power series for a completely different looking function. This is pretty cool stuff. So I think what we need to do now, I think we need to head back to the slides and see what is next.
All right, so that last example, we started to see the power of how, we can create a power series for 1 over x, and then we can use the power of that theorem to create power series for other functions. And we used the integration to get the power series for natural log x. So at this time to look at one of my favorite examples. This example is going to illustrate, hopefully, just how powerful this stuff is. How powerful we are creating math here. How we can create a power series. We're going to create a power series for an inverse trigonometric function in a very slick manner. We're going to be legally creative, but it's just using the power and how knowing one little thing can allow us to create and to actually be endlessly creative. So here's the example. We're going to determine a power series centered at c equals 0 for f of x equals inverse tangent x. And here's how we're going to do it. In part A, we're going to determine a power series for f of x equals 1 over 1 plus x. Part B, using what we come up with in part A, we're going to be able to determine a power series for the function f of x equals 1 over 1 plus x squared. In part C,
we'll be able to use what we come up with in part B to get a power series for f of x equals inverse tangent x. Really cool example. So let's head off to the chalkboard and crank through it. All right, folks, on this example, I think I prefaced this example by telling you it's one of my favorite examples. We're going to come up with a power series centered at c equals 0 for the function inverse tangent of x. And I kind of laid out, like parts A, B, and C, how to go about doing this. So part A, I said, we're going to first determine a power series for the function 1 over 1 plus x. Well, 1 over 1 plus x, since we're centered at 0, I don't have to worry about seeing an x minus anything. My goal is a over 1 minus r. It looks like that's immediately in that form. I'll write it like that. 1 minus negative x. A is 1, r is negative x. So we immediately have the function 1 over 1 plus x is the series negative x to the n, a r to the n. Or, if you prefer, it's kind of nice to see that as negative 1 to the n, x to the n. Since it's a geometric series, and we know geometric series converges when absolute value of r is less than 1, well, absolute value of r less than 1, absolute value of x less than 1, we immediately get the interval of convergence is negative 1 to 1. So let me write that down. Which immediately tells me, since we're centered at 0, the radius of convergence is 1. All right, so part A. We came up with power series for 1 over 1 plus x. Part B. It's the power series for 1 over 1 plus x squared. So 1 over 1 plus x squared. Folks, this is a function. You can evaluate functions at whatever you want. If I said to you, hey, look at this function. What's f of 3? You'd say, well, put 3 in for the x. That's what f of 3 is. What's the f of Sue? You'd say, well, put Sue in for the x. What's the f of x squared? Well, you'd put x squared in for the x. So if you know f of x is 1 over 1 plus x, and it has the power series to look at the f of x squared. You know what? Let me even put this in red. Just evaluating this function at x squared, we're just evaluating the power series at x squared. It's that old evaluating a function concept. Just substitute in. So this immediately gives us negative 1 to the n, x to the 2n. So we kind of did something very quick, but it went back to something old we know about evaluating functions. That we had this function, f of x equals 1 over 1 plus x squared. And I basically just said, hey, if you evaluate this function at x squared, you're putting x squared in for the x's, you get that function, so toss the x squared in for the x's in the power series, and we have our power series for 1 over 1 plus x squared. That's short, quick, friendly. How does that help us do part C? How does it help us in part C? Part C was get a power series. Oh, now we're going to get a power series for inverse tangent. Well, don't we know the derivative of inverse tangent is 1 over 1 plus x squared? Which means, don't we know the antiderivative of 1 over 1 plus x squared is inverse tangent? We know that. So it looks like all we have to do is take our power series that we have in part B, the power series for 1 over 1 plus x squared, and integrate it. Because we know the antiderivative of 1 over 1 plus x squared is inverse tangent. So we integrate it. And that immediately tells us let's see, I'll have a negative 1 to the n. When I integrate this, I add 1 to the exponent, and then 1 over that new exponent, the reciprocal of the new exponent, would be out front as a multiplier. So I add 1 to the exponent. It gives me x to the 2n plus 1. Then the reciprocal is out front. Inverse tangent, centered at 0, has that as a power series. Oh, and find the interval of convergence. I almost forgot the interval of convergence. Well, remember what the radius of convergence was from part A. We ended up saying the radius of convergence was 1. Part A, we had the interval of convergence negative 1 to 1. So you just have to check this at the endpoints. So I'll leave this up to you. You check at negative 1, you're going to get a series that converges. You check it at x equals 1, you're going to get a series that converges. I'll leave that checking up to you. So the interval of convergence is negative 1 to 1. Square bracket around both. Folks, that's really cool. It's really powerful what we just did. We just came up with a power series for inverse tangent of x. And we started off with getting a power series for 1 over 1 plus x. And then we evaluated that power series at x squared to give us a power series for 1 over 1 plus x squared. Then we integrated because we know the antiderivative of 1 over 1 plus x squared is inverse tangent. Really cool, really powerful. So here's what I'd like you to do. In your book, I'd like you to now try number 53. For number 53, I'm going to give you a hint. Look at, well, my hint is this example, part A. Look at what we have a power, in other words, we have a power series from part A for 1 over 1 plus x. I think that can help you quickly answer part B. So, or I'm sorry, answer number 53. So pause the video, use what we learned here for part A to help you do number 53. So pause the video, do 53. When you're done, restart the video. I'll be here at the board cranking through it. All right, folks, in number 53, you're asked to find a power series for g of x equals negative 1 over 1 plus x squared. Whoops. 1 plus x, the quantity squared. And the book says you're supposed to, and it's centered at 0. And the book said you're supposed to be using the function f of x equals 1 over 1 plus x. So here's what you'd have to do. You first need to come up with the power series for the function f, which is 1 over 1 plus x. We already know, in the last example, we came up with a power series for 1 over 1 plus x. So if, and I'm just writing down what we did in the last example. So what I'm saying is if we didn't already know that, that's what you would have to do first. You would have to come up with the power series for 1 over 1 plus x. You can't use that function unless you know what the power series is for that function. But since we've already done it, I'm just writing it down. Okay, now here's my first real quick observation. So it's just an observation. For the function 1 over 1 plus x, if I take the derivative of that function, I get negative 1 over 1 plus x quantity squared, which that's equal to the function I'm trying to get a power series for. So it looks like all I simply have to do is differentiate the power series for f of x equals 1 over 1 plus x. So if I were to string this out just a little bit, I know f prime of x is negative 1 over 1 plus x quantity squared, which, well, that's my g of x. Let's differentiate this. Let's do the derivative of it. We get the series negative 1 to the n x to the n minus 1. That's all. That's all there is to it. You have determined this function has this series. It's represented by that series, and we should check the we should determine the interval of convergence. So there is a little bit more to do. But remember when we did this, we determined the interval of convergence was negative 1 to 1. And remember that told us that our radius of convergence was 1. So all we have to do in this power series, all we have to do, it has the same radius of convergence as 1 over 1 plus x. When you do the derivative or when you integrate, it doesn't change the radius of convergence. It may change the interval of convergence only at the endpoints. So we just need to check the endpoints negative 1 and 1 for this. So we put negative 1 in for x, see what happens, put 1 in for x. And you're going to see when you check the endpoints, I'll leave it to you, that the interval of convergence is still negative 1 to 1. Powerful, powerful stuff. So we can use, we used a known power series for a function, 1 over 1 plus x, did a little bit of calculus, and created a power series for another function. This is powerful stuff. So that's the end of this video. This is the end of part 2 for section 11.2. So now you can do the rest of the homework in section 11.2 as well as the section 11.2 supplement number 2. Should be giving you plenty of practice for these problems. Thanks for watching.